For example, okay, got it. So no worries. It's a good point to start. So the science goals. What are the science goals of the SKA? So one important thing is the fact that since it's so powerful, so sensitive, this radio facility would be able to detect weak extraterrestrial radio signal if they were to exist. So of course, it's a very difficult task, but it's one of the science goal of the SKA. Try to look for extraterrestrial life with weak radio signal produced by these possible civilization around us. Another pillar is the cosmic magnetism. It's very difficult to study magnetic fields because they are not visible, and so just an instrument so sensitive as the SKA can do this kind of science on the large scales. But they can measure, for example, the polarized emission from synchrotron, and so infer what is the magnetic field or Faraday rotation, Zeeman splitting. There's a huge community that will use the SKA for magnetism. Another important thing more related to cosmology is like strong test of gravity. And one special... Was it the question?
Oh, yeah.
I cannot hear well. In case, maybe write on the chat.
Oh, please.
Sorry about that, I cannot hear. You can interrupt me later if the line is better, the connection is better. So one other important pillar is the fact that we can, with pulsar, measure the near, with pulsar try to measure, to do strong tests for gravitational, for gravity, because these are very extreme events, and so it's possible to do very precise tests for gravity using the pulsars. So this is one of a very interesting field where the SKA will really be different from the other, because it will detect a lot of pulsars, and so this test will be possible also on a statistical level. The two other that are most interesting for us are the ones that are kind of done with this 21 centimeter line of neutral hydrogen that we'll discuss in a second. And one is the really studying the full history of reionization, cosmic dawn and reionization. I will discuss this in a second. And this is something really possible only because the SKA can go so can span such a huge range of frequency, from going down to few megahertz to gigahertz. And from cosmology in itself, in like proper sense, what are the target of the SKA is kind of understanding the nature of dark matter, dark energy, of course. And one of the main probe that we can use is this 21 centimeter line. But of course, there are other projects on cosmology that I will not discuss today. For example, measuring radio weak lensing, or for example, using radio continuum surveys. So this is just to tell you how broad is the effort that the SKA will do and try to solve some of the scientific questions that are open. So what are we mostly interested in is this neutral hydrogen. And so I just wanted to recap a little bit what is the story of neutral hydrogen in a perspective of the story of the universe. So at the beginning, in the early universe, the universe was filled of this ionized gas. And then, as you know, there has been recombination. And so the emission of the CMB background. And at recombination, hydrogen became neutral again. So electron and proton that were free combined to form neutral hydrogen. And then there's the part that is called the Dark Ages, this thermal decoupling, where almost nothing is happening. So the hydrogen is just cooling down. And then at some point, the structures start forming, and what is called the cosmic dawn, because it's the beginning of the formation of the first stars and luminous object. The presence of this luminous object hits again hydrogen, and so hydrogen slowly reionize. So these proton and electron are disrupted again, and this is this full process called reionization, where the universe stops to be neutral and reionize completely again. So in the late universe, hydrogen in its neutral form is not present everywhere anymore as it was before cosmic dawn, but only in some neutral clumps here and there, and we'll see why this is important for us. But first, let me tell you about the 21 centimeter line. So what is, so it's one of the ground state of hydrogen. It's an hyperfine line. And so the lowest energy, you can see here in this picture here, the lowest energy has like these spins that are anti-parallel, and then tiny more energetic level has the spins that are actually parallel. So of course, when there is it is possible to excitate this line, so the electron occupies the higher line, and then by emission, a photon is produced, and the wavelength of these photons is exactly 21 centimeter in its rest frame, or if you want, in frequencies 1420 megahertz. So this is why it's called spin flip transition, because it's a transition between two levels that one has been anti-parallel and one parallel. It's a forbidden line, so it's very unlikely that this transition happen, and indeed it happens probably every 10 to the 6 years. But fortunately for us, hydrogen is the most abundant element in the universe, so we actually see a lot of 21 centimeter emission thanks to that. Okay, so why we always speak about frequency and the 21 centimeter line and redshift, and what is the connection? So the connection is that while in its rest frame, this 21 centimeter line is exactly 21 centimeter, well, it's a 21 centimeter emission line. While the universe expands, this line, the photon energy stretched, and so it change frequency, change wavelengths. So it's exactly the formula of the redshift. So we can reconstruct looking at the 21 centimeter line and another frequency. Exactly, we can reconstruct at which redshift it has been emitted. And for example, this is why we can reconstruct the history of a really big arch of the universe using radio waves. Because, for example, if you observe this emission 900 megahertz, that is exactly in the mid of the SKA mid-band, this will correspond to something that has been emitted at redshift 0.6. While, for example, if you observe a very low frequency, for example, with SKA low, 170 megahertz, we are already inside the epoch of reionization, so redshift around 7. If you observe even a lower frequency, for example, 70 megahertz, this will correspond to a period of the cosmic dawn. So when the first star starts shining, it's a redshift equal 20. So you can understand if we can span frequency from 50 to a few gigahertz, we can actually really reconstruct the history of the hydrogen all across its evolution from the cosmic dawn to up to now.
Sorry, Marta, please let me ask you a question.
Yes.
I don't know so much about this, but with this different frequency, why don't you think is another element that is emitting this frequency?
This is a good question. So it's a very clean line. So we know that there's not other line that pollutes this type of measurement. That is actually a problem for a lot of other intensity mapping experiment, for example, CO, C2. This is more complex because you can get confused and see other lines, but the 21 centimeter line is very clean. And so when you see something, you're sure that is the 21 centimeter line.
Okay, that's good.
Thanks a lot for the question.
Thank you. Yeah.
I also wanted to add for the students who have not seen cosmology yet. So when you talk about Z redshift in cosmology, that's a measure of time. So it tells you how far in the past you are. So large Z means far away in the past. But
exactly.
because time is distance, because light travels in a finite amount of time, far away in the past also means far away in the distance.
Exactly. So the cosmic dawn that are far away are what is called redshift around 20. The epoch of reionization starts after 20 and ends at redshift around 6, we think. And then everything that is after 6 is called post-reionization, and something that is redshift around 0.6 is considered what we can call late universe, and imagine something that goes up to 0, it's us.
Sorry again. So in continuation of Omadulu's question, so in this rest frame, it's 1420, but the redshifted is a wide range of frequencies from 70 to 900, as you're showing. None of these frequencies have a background?
Yeah, sure. It's one of the
Have a
hugest.
noise?
Yes, exactly. So this is one of the problem. I'm going to discuss for the rest of the talk exactly this
Okay.
problem. Because as I was saying before, there's not only the
Okay,
21 centimeter line emitting in this frequency, there's synchrotron, free. So there's nothing that looks exactly like the 21 centimeter line. So we cannot get confused at line level. But of course, there's all the other emission that we see from radio, that is the synchrotron emission, for example, from our galaxy.
Sure.
So this is what we'll be discussing the rest of the talk. Thanks for the question.
Oh, thank you.
So first, before entering in all the problems, I just want to finish discussing how powerful can be this 21 centimeter line and why it's important and how we can describe it in all the history of the universe. Sorry for the students, if you have questions, please don't hesitate to interrupt me. I'm very happy to discuss this. So the imagine that now we want to measure this. Imagine we don't have synchrotron, we don't have any of this foreground problem that we will address later. But we measure only this 21 centimeter brightness temperature. So it's called brightness temperature. So this is what we measure. But the temperature that we measure, how does it depends on everything that is going around? So it depends mostly on three fundamental temperature. So one, it needs something from the background. So in general, this background temperature is considered the CMB. So this cosmic microwave background. And then the two other important temperatures are the fact that these photons traverse a certain gas that has a certain kinetic energy, so the temperature of the intergalactic medium, and then this T-spin. T-spin is the temperature that regulates, that sets the population of this excited level at 21 centimeter. So it's TS is what in a sense give us how many electrons are in the excited level. So the combination of the evolution of these TK, T-spin, and the temperature of the CMB regulates how we do see changes in the temperature brightness when we measure it from our telescope. And this is how it looks like. So again, imagine this is a cut of the evolution of the universe going back in time, as Marcello was saying before. So this is us, late universe, and then we go back, reionization, this period here where a lot of things are happening, I'm describing in a second, down to the dark ages. And you can see the redshift below, and dark ages, so before the cosmic dawn is something redshift 50, and then at redshift 30-20 starts the cosmic dawn. So this combination of T-spin, T-gamma is what regulates in the end what we see as a temperature brightness for the 21 centimeter line. And for example, what is happening here is that at the beginning, the universe is very dense. So there is what is called collisional coupling. So the TS is almost at the same level of the temperature of the IgM, while the CMB is cooling down, but the EGM is cooling faster than the CMB. So the CMB is slightly hotter, and so this temperature starts negative. So I don't enter in all the details, but I just wanted to give you an idea that there is an evolution of this temperature brightness, and this evolution depends a lot on what is happening around hydrogen. For example, the universe expands and cools down, or the fact that the first sources appear, and so there is a lot of photons, for example, Lyman alpha photons that recouples a lot of the T-spin and the TK, and so there is this period where this temperature brightness is actually an absorption feature. But then when the universe heats up due to the presence of a lot of X-ray, finally this temperature brightness become in emission, and then this is all the period that we try to measure also with the SKA, all the reionization process. And in this part, T-spin is not very important anymore. What is important is this factor in front that is the fraction of the neutral hydrogen that is still neutral, or if you want, the fraction of neutral hydrogen that is not neutral anymore. And so there is a lot of these ionizing sources around, down to the latest stage, as that we were saying, there is almost no more neutral hydrogen around us, just some neutral hydrogen that has been, like in some clumps, has been shielded by the UV radiation. okay, indeed, this is what we see now. So now what we are seeing, imagine this is just a picture of the large-scale structure as we see them around us, and this is taken from a very famous paper, but this is just an illustration. So imagine these blue dots, so in the knots of this structure of the large-scale structure are places where we still have some neutral nitrogen left because the reionization process didn't manage to disrupt this neutral hydrogen. And so what you can also see is that if you remove the dark matter background and you look only at the blue dots, you kind of see that it traces similar structure. And this is why after the process of reionization, the presence of neutral hydrogen is considered a trace for dark matter. So it's a biased trace, it's called biased tracer, because of course it's not perfectly tracing the presence of dark matter, but the point is that we can use it to trace more or less where dark matter is. And so since, as we have discussed before, we can actually reconstruct the presence of neutral hydrogen at different redshifts, meaning different epochs of the universe, it means that we can do a thing called tomography. So we can scan different redshift, and if you can reconstruct the structure of the universe at different time, this is of course a great way of understanding something about the evolution of structure and thus dark energy.
Sorry.
Go for it.
Very basic question. So,
Thinking about someone else.
Okay. There's another question.
Yes, go for it.
Okay, I have a question about what you are saying, because I see what you are doing. About 21 centimeter is the redshift. So if for example, a hydrogen atom emit a radiation, for example, billion years ago, and this light emitted must travel and interact with other particle and decrease the frequency. So what my question is this: in your method, what you're doing, did you consider such kind of parameter and for correction?
Mm-hmm. Okay,
Yeah.
so you expect some of the signal to arrive up to us, and the idea is, as you were saying, it's emitted a certain time back in time, and then the universe expands, and so the frequency that you are actually seeing is not exactly the same one as it has been emitted. So yes. This is but then of course there's some you lose, and the one you lose you cannot do anything about that. But you have to try to understand what is all the other stuff that you are measuring. So of course you don't expect to see exactly everything, but at different epoch you're trying to see different things. For example, when you try to measure the patchy shape of reionization, there's a lot of things that you are not seeing. So you at different, let's say, it's a very difficult question because at different epochs there are different problems that you have to face. What I will mostly discuss is how much you don't see this signal, for example, at late time, and why. But of course there are plenty of other problems. But imagine that part of the signal arrives up to us.
Okay.
Marcello, what was your question?
Yeah, I was asking, so neutral hydrogen today mostly survives in the densest, so at the nodes of the,
Mm-hmm.
which is also where you have most stars, you know? So
Mm-hmm.
While all the hydrogen around were in the empty regions,
Mm-hmm.
all ionized. So how is this?
Yes, so the imagine that the reionization process is a very non-local process because these UV photons travels a lot to disrupt the structures. So I understand your question is that how can my hydrogen survive if there is a lot of star formation around? Of course, it's a balance. There is some part of this neutral hydrogen is disrupted in the process of star formation, but still the point is that the out from dark matter structure, it's very difficult that the hydrogen has survived. While in dense clumps, it's more possible that even if there is star formation going on, there is enough space for neutral hydrogen.
Much in the beginning.
Exactly. So if you, I don't have a picture, but if you look at the picture, for example, when they try to represent what is a reionization process, you have this huge bubble that expand and disrupt the neutral hydrogen on very large scales. And this is why it's a super difficult thing to simulate during reionization, because you have the local processes that are super important, but also you have to send your photons very far away. So you have to take this radiative transfer into account. And so this is why it's super difficult to simulate. Okay, so what are we trying to do with intensity mapping, and especially this low redshift part, is that in general, for example, how do galaxy survey try to measure the shape of the large scale structure? Well, they try to measure each galaxy, each single galaxy, and then using the position of all these galaxies, try to reconstruct the dark matter properties of the galactic this galaxy field. We cannot do that with intensity mapping, with 21 centimeter line, because the 21 centimeter line is very faint. So we can actually resolve a single galaxy in a very local universe, but then is resolve a galaxy that emits in H1 is super difficult at high redshift. So especially, I mean, imagine redshift 3, 4, it's really like an impossible task. It's possible, but it requires a lot of telescope time. So we have to find the balance between the fact that we want to see neutral hydrogen, but we also want to go large scale, because we are interested in cosmological scales. We are interested in how the universe evolves on these large scales. So the solution has been these 21 centimeter intensity mapping techniques that say, okay, let's look, instead of pointing a single point and try to resolve if there is a galaxy, let's just look at the big voxel in the sky and take all the signal that is arriving from that part of the universe. And of course, in that way, you are not resolving the single galaxy, but you will have a lot of emission of different galaxies in the same pixel. But this technique has the advantage that it's going to be cheap for large volume, because you just look at the part of the sky very quickly, everything that enters in your telescope, you collect it, and then you move to the next pixel. And so what is happening is that from a picture like a galaxy survey would see, that is something like this one on your left, you'll see something that looks much more like the one on the right. And for those who have seen a CMB map, this is quite similar to a CMB map. Of course, it's completely different physics. We are looking at different stuff. But the idea is to have these maps and then apply similar techniques to CMB to try to analyze it. So another important thing that we go for it.
Marta, okay, I understand that the main reason for intensity mapping is that it's cheaper, but otherwise, what would I win if I could resolve individual galaxies?
Well, it's a resolution. I mean, you will have, if you know the presence of hydrogen, well, not only resolution, you will gain resolution from a cosmological point of view, in the sense that here you're losing the small scales. Because you cannot resolve the small presence of each galaxy, so you're kind of smoothing everything with the fact that you are looking in this big voxel. So if you have a single galaxy, of course, you have higher resolution, so you have access to higher K. The other thing is that if you can resolve single galaxy, you will have a lot of statistics on cosmological scales, but also a lot of information on the baryon processes that are around these H1 galaxies. And of course, this will be great to have, because there's a lot of approximation you have to do if you want to use H1 as a bias tracer for cosmology, right? While if you have a lot of information on the H1 on small scales for all of these galaxies, in principle, there is much more stuff that you can understand. But it will require a telescope time that is too much for waiting for it, for us at least. Sure. So you have to find a compromise. Okay. So the other good thing that we were discussing just before is not only that we can go on this large cosmological volume, but it's not one single map, of course, because there is a map for every frequency that my telescope see, and these maps will correspond, as we have said before, to different redshift. So this is why we can reconstruct this called a tomographic view of the universe. And so in principle, combining SKA mid and SKA low, we can span redshift from us to redshift 6 with this technique, because it doesn't really work in the same way for the UR. So we will have to stay with this idea of measuring the landscape structure post-ionization, so after redshift 6. And this is a bit what we were saying before. The point is that during EOR, the physical process, the importance of baryons of these UV photons all around, it's much more important. So you cannot use a map in the EOR to trace the landscape structure in our cosmological sense, in the way we used to say for galaxy survey, for example. So that's why it's a post-ionization probe. You cannot use it during the ionization. You can, of course, do intensity mapping during ionization, during the cosmic dawn. It's just that you cannot easily then associate the presence of neutral hydrogen to the presence of dark matter and the landscape structure. So, but for the post-ionization is a measurement of the landscape structure. And as we were saying before, we have to be careful because it's not only a measurement of direct measurement of dark matter, but we are measuring this neutral hydrogen. So there's a lot of studies that we need to understand the connection. The other thing is that it will be very good in line of sight resolution, meaning that every frequency that the telescope can measure in principle can give me a different redshift, and then I could use them all. But then, since there is this intensity mapping technique and we cannot spend too much time on the same point, we will have this big voxel, and so the spatial resolution will be not so good. But I mean, we have to live with this compromise, and I think it's a lot of information that we actually have it. Oh, I'm a bit okay, in case I rush a bit at the end, or let's see. I've seen it, it's 34 already. So there's a lot of information that there are in the, of course, if I can measure the power, imagine we can measure the power spectrum of these 21 centimeter maps. For those who know what the power spectrum is, who don't know what the power spectrum is, it's just a measurement of the at which scale there is much power in my map. And when I do a power spectrum of something that is related to dark matter, there is a lot of information I can extract. Of course, on these high K, that are the small scales, there is, for example, information, very complicated information on the galaxy environment that we cannot, I mean, it's very difficult to understand, but still they're there. And then there are these wiggles that you can see in this blue line here. There are the baryon acoustic oscillation. So in principle, you can access this scale and measure the baryon acoustic oscillation with the 21 centimeter intensity mapping. And if you can go large volume enough, you can even start seeing this bending of the power spectrum that is linked to the matter radiation equality, and this would be a very something very beautiful to measure if it's possible. And so this is just to say that there is plenty of cosmological information even in summary statistic of these maps. So having these maps is a very powerful thing. But what is the problem? The problem is that this is what we would like to see. It's a signal that more or less we expect from simulation to be around few millikelvin, so below the millikelvin scale. But when we look at the sky, as we were discussing just before, we don't see directly this, but we see this huge, for example, emission from a galactic synchrotron in front of us that is order of magnitude higher. And here the scale is still millikelvin, and you can see that it's not below the millikelvin, but it's something like 30,000, can go up to 30,000 in the center of the galaxy. Of course, we try to avoid measuring directly in the center of the galaxy, but still it's super difficult to disentangle the two. And this is called the foreground problem. For it's one of the biggest challenge of 21 centimeter intensity mapping. And imagine the point is that you have this huge elephant in front of you and you would like to see the small cheetah behind, but you have to understand the elephant before you can arrive to actually measure your 21 centimeter signal. So the point is that there is a huge effort that we need to do in order to understand this foreground emission and try to find technique to get rid of this foreground emission, to disentangle the foreground emission from the one we want, and try to measure the 21 centimeter signal. So this is a a plot from a paper of Siambonga that is here in the audience. This is, for example, what is called the angular power spectrum. It's not really important for those who don't know what it is as a function of scale on the sky. What is important here to understand is what we want to measure is this black line here. And this black line here is order of magnitude lower than the other emission. So as we were discussing before, the galactic synchrotron. So of course, especially on large scales, the most powerful one is the map that we have just seen now. But then discussing the beginning of the talk, there's also free from both galactic and extragalactic free. So how do we do? It's not easy. There is some properties of the 21 centimeter can help in this direction. For example, imagine I took like one pixel. I take one pixel and I look at different frequency of this pixel. And imagine we know all the components that are inside, so we know the type of the foregrounds and the signal. And the good properties about the foreground is that they are much smooth in frequency with respect to the signal. So if I take, for example, one line of sight and I look at the evolution of the brightness temperature, I see that my foregrounds are quite smooth. So they evolve like a power law in frequency, while my signal oscillates like this black one here. So these properties can help to disentangle what is signal and what is foreground. And exactly the point is that if something is smooth in frequency, it means that it's very correlated in frequency. Instead, if you oscillate a lot, means that you're not correlated in frequency. So these two different behavior can be used to try to disentangle what is signal and what is foreground. There are various techniques. The two main ones are two big strategies that are called cleaning or avoidance. Foreground avoidance is mostly used for EOR studies, so I don't discuss it today, but I'll discuss mostly what is this foreground cleaning technique. Okay, so the foreground cleaning technique, this is a lot of words, but the main message is just in the formula on the top. So my temperature that I measure, it will be a combination of the signal I want to measure, some noise coming from the instrument, and then I imagine that that since I know that there are these foregrounds, I can describe this foreground as a combination of sources of different foreground. So this is these sources S and a mixing matrix A, linear algebra. Of course, this is not a simple problem to solve, and it's a very similar problem to a lot of other studies in astrophysics, in cosmology. For example, even the CMB has a quite similar problem to solve. So there are various ways of trying to solve this problem. One is trying to know something about how these foregrounds are behaving. This is what we were saying before, for example, the fact that they're smooth in frequency, so they have certain properties. And this is an approach, for example, that is quite used in CMB. It works quite well in CMB. And so there is for example, we know that the synchrotron should scale with a certain power law in frequency. Another thing is that, okay, I don't really assume physical properties for my sources, but I know something about them. For example, that they should be smooth, and so I can make assumption on that. Another completely different range of technique is called blind foreground methods. There's a lot of these methods. People went a bit crazy with the super different algorithms, and it's a sort of machine learning approach. So the easiest one, the most famous, and sometimes even the most powerful for our cases is the principal component analysis. But then there are others. So there is, for example, this fast independent component analysis has been used also for CMB, or GMCA, this generalized morphological component analysis. We don't really need the details, of course, just that there are a lot of different algorithms that try to solve the same problems. So just for those who are not familiar with that, I am going to just spend 1 second on PCA. And so of course, there's some trick you have to do in the way we deal to our data to use the PCA, but the most important thing that you need to remember is that the assumption that we are making is that since the foreground are strong, we can describe the foregrounds with only few modes, principal components, let's say, and we can kind of imagine that the shape that this foreground have in this space that we are describing in the data actually need only a subspace of these variables to be described. So for example, I think this is a good example. Imagine our foregrounds don't need the full 3D plane, but they are well described by a 2D plane. So these are techniques that help us to say, okay, so the foreground lies on the 2D plane. I can describe the foreground only in that 2D plane, and everything that is left will be my signal. So this is what is called, in general, what is called the number of foreground that we subtract. And so this is called this n foreground. And the more we think that there are components in the foreground, then the more we have to keep of these principal components to describe the foreground, and then everything that is left will be our signal. So it's a sort of PCA, but used in a different sense for 21 centimeter intensity mapping, because the principal components will be the foreground, and what we are interested in is everything that is left, that will be our signal, that we are not capable of describing with only these few modes because it's more complicated. So maybe I didn't really clarify it, but I hope the main idea here is that there is one number that you have to remember, that when we do this blind cleaning, there is this number of foregrounds that we subtract. This number of foregrounds is exactly the number of, in a PCA language, the number of principal components term that we have kept for describing the foreground. So normally,
you made the example of the plane because you expect most of the foreground to come from the galactic plane, or?
Oh no, just because it's yeah. So it's another. It's not a space properties. It's a properties of frequency matrix. That's why it's a bit difficult to visualize. Actually, it's very simple when you do it. It just takes the time of doing it once, but explain it without having doing it, it's a bit complicated. But so it's a frequency matrix that you construct, and then your foreground have are very strong, so you can assume that it's easier to describe them with only few modes in this frequency matrix, and everything else is your signal.
Okay.
So the only important number to remember is that people will talk a lot about this number of foregrounds. When you will see a 21 centimeter talk, there will be this number of sources that we have subtracted. So this is only related to the jargon of the PCA, of fast ICA, of subtracting these modes to clean the signal. Of course, it's a big jump to assume that this is actually working, and indeed this needs to be carefully checked with simulation. And here I put two examples. One is again from a paper of SIA. So the idea here is that I simulate the foreground plus the signal. I run this cleaning technique, and I see a change in the number of foreground that I subtract if I can actually reconstruct the signal. So your signal here, you don't really need the details. This is a line of sight power spectrum. We don't care. The H1 that I want to reconstruct is this red line. And if I do my machinery with different number of foreground to subtract, if I subtract 3, I don't subtract enough. If I subtract 5, I subtract too much. If I subtract 4, apart from these scales here that I have to assume that I will naturally lose for properties of the foreground and how PCA cleans this foreground. But apart from that, I can reconstruct very well the signal. So this is good news. In simulation, it works. I have just to be sure what is the number of foreground that I have to subtract. So what we did, for example, with the intensity mapping SKA focus group, we said, okay, let's construct a very difficult simulation and try to see if people can actually reconstruct the signal. And this is, for example, an example from that, all different lines. So the black line is what I want to reconstruct, and all these different color lines are the results from different people, what they try to reconstruct. So the main message is that in simulation it's difficult, but it works. What about real data? Well, in real data is not so easy, because there is a lot of these things that enter in the components that we cannot actually understand very well. And this is a plot from a paper of Laura Waltz that shows that GBT data, if you try to clean them, so the signal is expected to be much lower than this plot. And even if you try to clean them and you use a lot of component to subtract, so up to 36, for example, it's still very high, the signal. So you clean, but you're never cleaning enough. Why you're not cleaning enough? Because there's a lot of components in the signal that are difficult to understand, and we cannot simply clean in this way. So the lower part here is just when, instead of using the same map from GBT, I use a map of GBT in another period. And so there are some systematics that concern the instrument that varies from period to period when you do the different map. So at least when you use a cross correlation between map of different period, you go a bit down with the signal. So remember, what you want to do is the signal is expected to be much lower than here. So the more you go down, the better it is. So you can kind of try to go down a little bit, cross-correlating different times, maps from different times, but the problem is still very important. And you see that before in the simulation, n equal 4, 5 was working, and here 36 is not working with real data. So there is still a huge problem to solve, try to understand what are these spurious contamination from data. Of course, another solution is that you will have to have a better instrument. That is what we want to do with the SKA. So how is the way out of this problem? So there are two things. On the long run, we need to understand the instrument. So GBT now maybe is arrived at its best, but for the SKA, we will need to, when we have this kind of problem, we need to understand why the instrument is so complicated to describe, why we cannot clean the instrument, the foreground contamination, just how it works in with simulation. The other technique that is quite used is the fact that there is a way of trying to avoid all these problems of foreground contamination. And it's the fact that instead of using simply the 21 centimeter signal, you cross-correlate the signal with galaxy. So very briefly, because I'm already a bit out of time, the point is that if you cross-correlate a map from galaxy with a map from 21 centimeter signal, all the contamination for foregrounds does not correlate with your galaxy map, and so it goes away. So this is simply like that. So since your optical map will have the signal plus the noise, and your H1 map will also have signal plus noise plus residual foregrounds plus contamination, as we were seeing in the plot before, when you cross-correlate the two, everything that is not correlated goes away. And hopefully these residual foregrounds, the residual systematics, are different from the galaxy survey to the 21 centimeter intensive mapping maps, and so they goes away. And indeed, it has been possible to measure the 21 centimeter signal in a lot of experiments in this way. For example, GBT cross this DEEP2, that is a galaxy survey, or Wiggle Z, that is another galaxy survey with GBT, but also the Parkes telescope in Australia with another galaxy survey. And more recently, one of the plots I was showing comes from this GBT cross BOSS and Wiggle Z cross correlation. So cross correlation kind of solves the problem of the foreground contamination, but in principle, we would like to have also detection of the 21 centimeter itself without having to resort to using galaxy survey. So this is what the MeerKAT and the SKA in the future would like to do. And so let me spend my last 5 minutes. Can I have other 5 minutes, Marcello? Yes.
Sure. Yeah.
Okay. In the last minutes, I just described what is this project, that a South African-led project. The PI is Mario Santos, that is at UWC. There is Brandon here and Sia that are part of the experiment. So the idea is to use the MeerKAT telescope, that is one of the precursor of the SKA, meaning that it's already in the site of the SKA and will actually be part of these 64 dishes that are already built for MeerKAT will be part of the SKA 200 dishes. And this is not a picture, this is actually a photo, so it's already there, it's taking data, and you can see it also from a satellite vision. So the point is that this is a super powerful experiment. I don't have time to enter in the details, but there's a reason why radio astronomy likes interferometers, and the reason is that you cannot, that if you have only one dish, there is a limited resolution on the sky that you can have. But if you can use combination of different dishes, you can actually have resolutions that are very small, very high resolution, and this resolution depends on how far you can put your array. So the larger you can go in how far are two dishes in an array, the better resolution you have on the sky. This is not exactly what we need for cosmology, because for cosmology what we want is to measure the large scales, and to measure the large scales you cannot you cannot do that with the super small resolution. So the way out that has been thought, Mario Santos has been one of the promoter of this thing, is to use instead of MeerKAT as an interferometer, MeerKAT as a collection of single dish. So the resolution on the sky will depend on the dish, but the scales that this telescope will resolve are exactly the large cosmological scales that we are interested in for the last case structure. So this is just some technical information that we actually don't need, but this is the most important thing to remember, is that we are measuring with MeerKAT some patches in the sky with 64 dishes. For the moment we are at this slightly high frequency, meaning that we are only measure things out to redshift 0.5, 0.4. In principle, we would like to go to higher redshift because there's a lot of information at the higher redshift we would like to measure. So we hope to be able to do that in the future. For the moment, this range of frequency is called L band. Band 2 in SKA jargon, and for the moment we are doing observation there. Of course, there is a big plan of using this MeerKAT for intensity mapping, is called MeerKAT, to have even larger area. For the moment we have not 300 degrees square. That is not a lot for cosmology, but this is our first verification data. And of course the biggest area will be super useful to arrive to bigger scale and so for cosmology. And the plan possibly is while we do intensity mapping, we also measure this radio continuum in H1 galaxies, and these are other science goals that can be done together with the cosmology, and this is called commensality. So this is what we have up to now. This is our map of a part of the sky. The strange shapes come from how the observations are done. That is, the telescope is a fixed declination and moves like that. So in the end, in Radek comes with these strange stripes. And this is a map from Wang et al. That Jing was a postdoc in UWC up to last month. So it's a very UWC led result. And so this is the actual map of the sky, calibrated, successfully calibrated. And as we were discussing before, the first thing we are measuring is the galactic synchrotron. So this is actually a map of galactic synchrotron at the moment, but we try to clean it. So this is like a very easy attempt to do this cleaning. And you can see that if you clean at least if you remove the galactic emission, you see that there are emissions from port sources where you expect them. And so this is good. There are actually studies at the moment that are going on to cross-correlate this cleaned map with WiggleZ, that is a galaxy survey, and we are optimistic on the fact that we can actually see a signal. Of course, there's plenty of things that are not working. I'm just put a list here just to give you an idea of how difficult it is to do this measurement, because you have to take into control the beam. This way of scanning the sky gives you an inhomogeneous noise. You have to take this into account, and then you have a lot of RFI that force you to like throw away a lot of information, because they are too much contaminated by terrestrial interference, by satellites. Brandon here on the call is an expert of how much we have to throw away data because of geostationary satellites that corrupt our map. And so just to finish, I wanted to say that we are trying to simulate all this, to do a big effort to construct a very realistic simulation and try to challenge cleaning methods on realistic simulation, so that we can kind of bring this simulation at the level of the data. And this is what we have done in a project in these last 2 years with a lot of people from a bit everywhere, and also from South Africa. So we have constructed this huge simulation, and we have run a blind challenge, meaning that we didn't say to people what was the level of each one, and we said, try to use your favorite cleaning methods and tell me what you think is the level of the signal. And so the results have been goodish, let's say. So the only thing I want you to concentrate is the fact that this figure here should be white if everything went well. So anything that is not white means that the cleaning didn't go as expected. So this is the angular power spectrum in the sky is a function of frequency, and you can see that at certain scale, at certain frequency, there is still struggle, even in simulation, when the simulation is a bit more realistic for this kind of cleaning. Of course, this type of challenge are super important because we need to understand which method performs better, and ultimately we need to try to trust what is the result, because in the real life we will not have simulation to tell us, oh yes, you cleaned properly or you don't. So we need to really be careful and understand how well this foreground cleaning works, try to assess if we can trust them or not. So I conclude in this first slide of conclusion on the fact that this strategy that we have used of this blind testing has been actually very nice to test, because you can see how mature the various pipelines from the group around the world are to try to clean this foreground from intensity mapping surveys. And of course, the point is that they are powerful, but we need to work more on how to use them. And of course, on the other side, we need to look at instrumental effect, especially studying MeerKAT data. So that is intensity mapping survey from MeerKAT, and try to construct in the simulation the same challenges that we see, the same systematics that we see in the data. And so we have a lot of future projects. We need to add more MeerKAT sparse systematics, parameter inference, and then study cross-correlation with other probes. There's a lot of ideas and a lot of space if people want to join the effort, of course. I just leave you with this, my conclusion, that our 21 centimeter cosmology still have to prove its full potential, but has an enormous potential, as we described, on how much arc in the history of the universe can actually be spun using the 21 centimeter line. There are data already, there are data from previous telescope, and there are data from MeerKAT now to analyze. And of course, we are doing an effort to understand the instrument and the analysis pipeline, and we need a lot of simulation. And all this effort, hopefully, will bring us ready when the SKA facility will be available, and we will have much more time of the telescope to do these intensity mapping surveys. So we'll have big areas and a lot of signal, hopefully, to analyze. And yeah, I take question. Thanks a lot. Sorry, I went a bit long.
Thank you, Marta. Right on time instead. Thank you. Yes, do we have questions from the audience? Very nice talk.
Don't hesitate, please. I'm happy to take question. And if I wasn't clear, just tell me. I go back on some slide.
Any question is welcome. Maybe I have.
Yeah.
Oh no. Okay, please.
Question, please. That about the 21 centimeter signal. This is a signal which emitted from the source, not what we detect or observe here. Yeah. So the antennas of the MeerKAT, the dishes, actually measure or detect longer wavelengths. Yeah.
Yeah. So exactly.
Right.
So we can detect. So the 21 centimeter signal, it's at 1.4 gigahertz, right? In the rest frame. So since the span of the SKA frequency, it's from 50 megahertz to tens of gigahertz, you can actually also detect H1 very around you. So this is, for example, this is not. It's difficult to use this for cosmology, but a lot of people have, for example, that studies in particular H1 galaxies, they can do that. So they take the telescope, they resolve an area, a particular area, and measure an H1 galaxy, and really resolve the inflow and the outflow and how the hydrogen is moving in the galaxy at local redshift, because you can have 1.4 gigahertz. Then if you try to measure at lower frequency, of course, you have, I'm saying there is a lot of other emission. There is all the radio emission you are also seeing. But if you measure from 1 gigahertz to 50 megahertz, part of the emission you're seeing with your telescope will come from the fact that the 21 centimeter line emitted locally by the natural hydrogen arrived to us stretched by the expansion of the universe at lower frequency. So for example, as we were saying, 500, if I really can measure 50 megahertz, I would measure a 21 centimeter signal that comes from the cosmic dawn. But of course, as I was saying, it's difficult because there's other radio emission in the same frequency band. But in principle, you can measure also the local H1 up to very far H1 back in the past.
Thank you. So second question, please, that if this project is candidate to measure something like the Hubble parameter to study the rate of the expansion of the universe.
Yes,
one of its aims as study dark energy and the logical structure evolution. Yeah.
It is. So I didn't go into the details because I wanted more to give you the idea, but this is a very good question. Sorry, I should have put a backup slide. So in principle, for example, exactly as you do with galaxy survey, if you can measure the BAO, you can measure the angular diameter distance and h of z. So how h of z evolve as a function of redshift. So yes, since you have the power spectrum at different redshift, this gives you a way of constraining h of z. So of course you can measure the evolution of the Hubble parameter like that. Sorry, I didn't enter in the details. Of course, you need first to measure the 21 centimeter power spectrum, and this is one of the challenge. But one of the things you can do is you can measure h of z. So there are forecasts that says that with SKA we can measure h of z almost as good as Euclid, for example, will do. A bit like with less power, but on a larger redshift range.
Thank you very much.
Thank you.
Okay, I have a question related to what we were talking. My question is related to during your presentation. You on one slide you are talking about power spectrum, and I didn't know if the technical part, as I know, power spectrum is the Fourier transform of maybe energy density tensor, something like that. And if you present that and your detector will detect only 121 centimeter or will detect all frequencies, because power spectrum is Fourier transform, it contain all modes of this. Yeah.
Yes, exactly. So what I showed, so the power spectrum is the Fourier transform of the two-point correlation function. Imagine that you have a sort of slice on the sky. Okay, so you can construct the power spectrum on these different slices, and so you will have a power spectrum computed at different redshift. So you will have a sort of, so your measurement in principle has a very fine redshift resolution, but for signal to noise reason, you will sum up a bit of map, and so you will have like slices in a different redshift, and then there you can construct an effective redshift your power spectrum. So you will have one measurement of the power spectrum for each effective redshift beam that you want to construct with your data. So of course, people normally say that we could use, for example, a delta Z of 0.1 to compute the power spectrum. Let's see if we can actually do it with the signal to noise that we have from the data. But so this is the idea, right? So you will construct a P of K for every effective redshift. It's like a little bit, for example, the BOSS collaboration, they have low Z and CMAS, they have two different redshifts, they compute power spectrum, actually parameter, the derived parameter at these two different redshifts. But in principle here, with 21 centimeter analysis, you can construct different power spectrum at different redshift. So you will have various power spectrum, and so you can see the evolution, and that's why it should be super powerful for dark energy.
Okay.
Thanks.
When you do the challenge, so you give out the simulated data, right? So does that include instrumental effects?
Yes, so we tried. So that's why. Sorry, I went a bit fast, but we tried to at least put inside the simulated effect the more common that we knew. For example, we one of the things we put is this beam shape that is not the standard Gaussian one that people normally have used, and this is something that SKA did in his paper. So considering, for example, the fact that your beam is not just Gaussian but has side lobes. And so we put a realistic beam inside the simulation. Then we put the fact that the noise will be quite strange because your scanning strategy will not be homogeneous. So it's not. So there will be points in the map where you pass more, and the more peripheral points of the map where your noise is higher. So you have to take these into account. And then what we are trying to do now is to add more and more systematic effect, and not only the beam and the noise, but for example the presence of residual satellites, or for example remove some chunks of the data due to RFI, so these kind of things. And we are trying to challenge our cleaning data on that, cleaning algorithm on that.
Okay, so all these effects are actually independent on the instrument.
Well, the beam it's the shape of the instrument, and then for example you have to take into account, I don't know, the fact that in principle you can take into account the more related to the instrument, the fact that your noise is not only dependent on how many times you pass in the sky, but will depend on how your instrument system temperature evolves with redshift, for example. So the instrument enters in this sense. Or for example, one thing at some point we wanted to look at is the fact that when you actually take this measurement, you don't only have the emission from the sky, you have also emission from the soils that enters in your antenna, and then you have to take this into account. So you need to learn how to minimize these and how to be sure that there's not ground emission left in your data.
But then, nevertheless, the other people who have to guess the simulated data, so to clean the simulated data, they have to guess which instrumental effects you have.
Yes. Yeah. So in principle, exactly. So in principle, one of the great promise of the blind methods was that you don't need to know much. The blind method will do it by himself, right? And it was not exactly what we found. So we need to work more to trust completely the blind cleaning.
Okay. Yeah. Good. So do we have more questions? We have ambulance.
Yes, sorry.
Okay, I don't know if there are more questions from the audience. Your chance is now. Otherwise, I think we can probably.
No, you can write me.
Or Marta, or write to me, and I will send Marta's email address. Okay, so otherwise, thank you very much for the very nice talk.
Thank you.
I hope the other people see it. And thank you.
Bye, thanks a lot, and bye to my UWC people around. Ciao, guys.
Thank you. Bye.
Thank you very much.
Bye, thanks.